According to the 2020 National Electrical Code, specifically Section 250.66c3, the minimum size of a copper grounding electrode tap conductor for a separately derived alternating current system involving 3 sets of 300 kcmil secondary conductors is 2/0 American wire gauge. To elaborate on this requirement, it's important to understand the function of a grounding electrode conductor, often referred to as the GC. The grounding electrode conductor connects the system's grounded conductor, or the equipment grounding conductors, or both, to a grounding electrode. This electrode provides a low impedance path to earth, facilitating the clearing of ground faults and ensuring the safety of personnel and equipment. Separately derived systems, commonly found in transformers and generators, require a dedicated grounding electrode conductor to establish a reliable ground reference. The size of the grounding electrode conductor is determined by the size of the largest ungrounded conductor of the system. However, in situations where multiple conductors are present, as in the case of multiple sets of secondary conductors from a transformer, a specific calculation is necessary to determine the appropriate grounding electrode conductor size. Section 250.66 of the NEC provides the guidelines for sizing grounding electrode conductors. In most cases, the size of the grounding electrode conductor is based on the size of the service entrance conductors. But for separately derived systems, subsection C provides specific rules. When dealing with multiple sets of secondary conductors, as outlined in 250.66c3, the code mandates that the grounding electrode tap conductor be sized based on the equivalent size of the combined secondary conductors. In the specific scenario of 3 sets of 300 kcmil secondary conductors, we must determine the equivalent size of these conductors when combined. To determine the equivalent size, we first need to find the total circular mil area of the 300 kcmil conductors. Since kcmil represents 1000 circular mils, each 300 kcmil conductor has an area of 300,000 circular mils. With 3 such conductors, the total circular mil area is 3 multiplied by 300,000, which equals 900,000 circular mils. Now, we need to find the conductor size that corresponds to 900,000 circular mils. Consulting the NEC, specifically Chapter 9, Table 8, which provides conductor properties, we can determine the appropriate conductor size. Alternatively, standard conductor ampacity tables can be consulted to find the conductor size that corresponds to an ampacity close to what would be required for 900,000 circular mils. Keep in mind that the ampacity of a conductor is related to its circular mil area, with larger conductors generally having higher ampacities. Based on conductor property tables, a conductor with a circular mil area of 900,000 would necessitate a grounding electrode conductor larger than 1/0 American wire gauge. Typically, a conductor size of 2/0 American wire gauge or larger would be required to meet the circular mil area requirement. Therefore, the minimum size of the copper grounding electrode tap conductor for the separately derived alternating current system with 3 sets of 300 kcmil secondary conductors is 2/0 American wire gauge as per NEC Section 250.66c3. It is important to always refer to the latest edition of the NEC and consult with a qualified electrical professional to ensure compliance with all applicable codes and standards. Grounding electrode conductors play a vital role in electrical safety. They provide a path for fault current to return to the source, allowing overcurrent protective devices, such as circuit breakers or fuses, to trip and de-energize the circuit. This helps prevent electrical shock hazards and equipment damage. Proper sizing of the grounding electrode conductor is essential to ensure that it can safely carry the available fault current. If the grounding electrode conductor is too small, it may not be able to handle the fault current, which could lead to overheating and potentially a fire. In addition to the size of the grounding electrode conductor, it is also important to ensure that it is properly installed. The grounding electrode conductor should be connected to a grounding electrode, such as a ground rod, ground plate, or metal water pipe. The connection should be made in a manner that ensures a low impedance path to ground. The NEC provides detailed requirements for the installation of grounding electrode conductors and grounding electrodes. It is important to follow these requirements carefully to ensure a safe and effective grounding system. Here are some additional considerations for grounding electrode conductors. Firstly, the material of the grounding electrode conductor must be copper, aluminum, or copper-clad aluminum. Copper is the most common material used for grounding electrode conductors due to its excellent conductivity and corrosion resistance. Secondly, the grounding electrode conductor must be protected from physical damage. This can be achieved by running the conductor in conduit or by using a listed grounding electrode conductor clamp that provides physical protection. Thirdly, the grounding electrode conductor must be continuous and without splices or joints. If a splice or joint is necessary, it must be made using a listed connector that is suitable for grounding purposes. Fourthly, the grounding electrode conductor must be connected to the grounding electrode in a manner that ensures a permanent and reliable connection. This can be achieved by using a listed grounding electrode clamp or by exothermic welding. Fifthly, the grounding electrode conductor must be sized based on the largest ungrounded conductor of the system. Table 250.66 in the NEC provides the minimum size requirements for grounding electrode conductors based on the size of the ungrounded conductors. Sixthly, the grounding electrode conductor must be installed in accordance with the NEC. The NEC provides detailed requirements for the installation of grounding electrode conductors, including requirements for the type of grounding electrode, the location of the grounding electrode, and the method of connecting the grounding electrode conductor to the grounding electrode. In addition to the above considerations, it is also important to consider the following. Firstly, the type of grounding electrode used. The NEC recognizes several different types of grounding electrodes, including ground rods, crown plates, and metal water pipes. The type of grounding electrode used will depend on the soil conditions and the availability of suitable grounding electrodes. Secondly, the soil conditions at the site. The soil conditions will affect the resistance of the grounding electrode. In general, lower soil resistance is better. If the soil resistance is too high, it may be necessary to install multiple grounding electrodes in parallel. Thirdly, the local codes and regulations. Some local jurisdictions may have additional requirements for grounding electrode conductors and grounding electrodes. It is important to check with the local authorities to ensure compliance with all applicable codes and regulations. In summary, the correct sizing and installation of grounding electrode conductors are crucial for electrical safety. It is important to follow the requirements of the NEC and consult with a qualified electrical professional to ensure that the grounding system is safe and effective. When installing or maintaining electrical systems, always prioritize safety and adhere to the latest edition of the National Electrical Code. Regular inspections and testing of grounding systems are recommended to ensure their continued effectiveness. Remember that electrical codes and standards are subject to change, so staying updated on the latest requirements is essential for electrical professionals and anyone working with electrical systems. Consider enrolling in continuing education courses or attending industry seminars to stay informed about the latest developments in electrical safety and grounding practices. In addition to the specific requirement of 2/0 American wire gauge for the given scenario, it is crucial to understand the broader context of grounding and bonding in electrical systems. Grounding and bonding are two distinct but interconnected concepts that work together to ensure electrical safety. Grounding refers to the connection of electrical equipment and systems to the earth. Bonding refers to the connection of metallic parts of an electrical system to create a low impedance path for fault current. The purpose of grounding is to provide a path for fault current to return to the source, allowing overcurrent protective devices to trip and energize the circuit. This helps prevent electrical shock hazards and equipment damage. The purpose of bonding is to minimize the voltage difference between metallic parts of an electrical system. This helps prevent electrical shock hazards and reduce the risk of fire. Grounding and bonding are essential for electrical safety in all types of electrical systems, including residential, commercial, and industrial systems. The NEC provides detailed requirements for grounding and bonding in Chapter 250. It is important to follow these requirements carefully to ensure a safe and effective electrical system. Here are some additional details about grounding and bonding. Firstly, grounding electrode system. The grounding electrode system consists of the grounding electrode and the grounding electrode conductor. The grounding electrode is a conductive object that is buried in the earth and provides a connection to ground. The grounding electrode conductor connects the grounding electrode to the electrical system. Secondly, equipment grounding conductor. The equipment grounding conductor is a conductor that connects the metallic parts of electrical equipment to the grounding electrode system. The equipment grounding conductor provides a low impedance path for fault current to return to the source. Thirdly, bonding jumper. A bonding jumper is a conductor that connects two or more metallic parts of an electrical system together. Bonding jumpers are used to minimize the voltage difference between metallic parts and to provide a low impedance path for fault current. Fourthly, ground fault circuit interrupter. A ground fault circuit interrupter, also known as a GFCI, is a device that is designed to protect people from electrical shock hazards. A GFCI monitors the current flowing in a circuit and trips the circuit if it detects a ground fault. Ground faults occur when current flows through an unintended path to ground, such as through a person's body. Fifthly, arc fault circuit interrupter. An arc fault circuit interrupter, also known as an FSI, is a device that is designed to protect against electrical fires. An FSI monitors the current flowing in a circuit and trips the circuit if it detects an arc fault. Arc faults are caused by damaged or deteriorated wiring and can generate high temperatures that can ignite nearby materials. In conclusion, a thorough understanding of grounding and bonding principles, along with strict adherence to the NEC, is essential for ensuring electrical safety. The specific requirement for a 2/0 American wire gauge grounding electrode tap conductor in the described scenario underscores the importance of accurate calculations and code compliance in electrical installations. Always consult the latest edition of the NEC and seek guidance from qualified electrical professionals to maintain a safe and reliable electrical system. Remember to regularly inspect and test grounding and bonding systems to ensure their continued effectiveness. Staying informed about updates to electrical codes and standards is crucial for all electrical professionals and anyone involved in electrical work. This commitment to safety and knowledge will help prevent electrical hazards and protect people and property. Always prioritize safety when working with electricity and follow all applicable codes and regulations.